This is a quick Ampere-Faraday Lenz law demonstration using a primary coil that's plugged in. So I'm in the United States, so it's hooked up to a 60 Hertz AC power source. And then in the primary coil, there's rebar, and the rebar is nestled in a PVC pipe. And then on the outside of the rebar, I have an aluminum ring, so it's non-magnetic. It's not magnetic itself. So if I turn on current in the primary coil, the oscillating current in the primary coil creates an oscillating magnetic field, and the oscillating magnetic field induces a secondary current in this ring in such a way that you always get a repulsion. So this picture represents the solenoid hooked up to a 60 Hertz AC power supply, and this picture represents the ring. So this, as I said over there, there's going to be an oscillating current in the solenoid that's going to produce an oscillating magnetic field, and that oscillating magnetic field is going to induce a secondary current in this ring. So let's look at the physics behind how we always get a repulsion so that the ring shoots off. So if we start with our primary statement up here, that the current is a cosine function or some kind of sinusoidal function. Because we're in the United States, this number is 60. If we were in Europe, it would be 50. Using Ampere's law, we get the magnetic field as a function of time in a solenoid to be this. Then using Faraday and Lenz's law, we get the induced EMF in the secondary ring to be this as a function of time. Taking the derivative of this cosine function, we obtain this for the EMF induced in the ring. Then, if you're an electrical engineer, you know the acronym Eli the Iceman. And so what that means is that the EMF, or the voltage applied around the ring, precedes the current by 90 degrees. So a 90 degrees or a pi over 2 phase shift. And so the current that's induced in the ring lags the voltage by 90 degrees. And so this is the function for the current induced in the secondary ring. Well, as you know from your trig, the sine of some value times t minus pi over 2 is the negative cosine. And so if we come over here to the graph, we see that the primary current is always going to be opposite to the secondary current. And another thing that I'm not proving here is that anti-parallel currents repel one another. And so, from the physics, from Ampere's law, Faraday's law, and Lenz's law, we predict that we should always get a repulsion between the secondary current and the primary current. Thank you for watching. Current in the graph. Okay.